Okay, so welcome to the beginning of our online video lecture on Chapter 22 on electromagnetic waves. I think this figure does a good job of explaining why we might care. So we just spent all this time laying some fundamentals about waves in general. And now we're going to talk specifically about the kind of wave that we've been building to for this whole semester, which is electromagnetic waves. They've got electricity in them and they've got magnetism in them. So these are going to be sort of the grand unifying theme of understanding why electricity and magnetism are really just two different manifestations of the same thing. And of course, it's appropriate to have a picture of the moon on here because one thing that is unique about electromagnetic waves compared to waves that we have discussed in previous chapters is that electromagnetic waves travel through space. So there's no need for a medium like a rope or air as in a sound wave or any of the other kinds of waves or a spring or any of those things. There's no reason for a medium to be present for an electromagnetic wave to propagate. All right, so we're going to talk a little bit, or quite a bit actually, about how antennas work. So this is an antenna receiver, and actually one thing that you may not have ever noticed about it if you've not really gotten into radio type things is that actually there's tons of different bars on this antenna, and all of the different bars have different lengths on them. And this is actually going to be so that this antenna can be resonant with electromagnetic waves at a whole bunch of different frequencies. So we'll do an example later about why those antenna bars are all different lengths. And we'll just sort of learn some general properties about electromagnetic waves and try to make some connections between maybe visible waves or radio waves or microwaves, the types of waves that you're kind of comfortable with and familiar with and aren't really afraid of being exposed to, compared to things like, say, gamma rays or X-rays, which you know to be at least a little wary of being exposed to. And just to remind you a few things that we just covered, so hopefully they haven't gotten too rusty. So we learned about properties of traveling waves. So for sinusoidal waves that are undergoing simple harmonic motion up and down in the shape of sines and cosines, wave speed is the product of the frequency and the wavelength. So I'll break the rule and write on this just for a second, which is what we just said, which is that the speed of the wave, which for light waves we're going to actually call a c here, instead of it being a v, to specifically denote that we're talking about light waves or electromagnetic waves, depends on the wavelength times the frequency. And that's been an important equation so far, and it is going to continue being an important equation going forward. All right, so let's start off with an example that is really a Chapter 22 example because we're talking about electromagnetic waves, but there's nothing that requires this to be an electromagnetic wave. So I have a microwave oven, uses 2.4 gigahertz as the frequency of those microwaves. A cell phone also uses electromagnetic waves. It operates at a little lower frequency, 1.9 gigahertz. So which one has the bigger wavelength, or are they equivalent? Give you a minute to think about that. Okay, so this is going to come from this equation here that we have, which is that just like when we were doing things with sound, it was always that the speed of sound was constant, and we varied wavelength and frequency in order to make speed of sound be constant. Now the speed of light is what's constant. That is an unvarying thing. The speed of light in a vacuum is a measured quantity. It's known very precisely. So whatever is happening to wavelength and frequency has to give rise to having a constant speed of light. So if we want a longer wavelength, there's our longer wavelength, then we need to have the one that has the smaller frequency, and that is the 1.9 gigahertz wave. A little bit about just sort of how you describe these things. The way that we talk about frequency and wavelengths can be a little bit confusing. We tend to talk about long and short wavelengths. So a long wavelength, that would be a big number. And then we tend to talk about high and low frequencies. So you can kind of trip yourself up a little bit if you're not careful about sort of what a long wavelength means. You might think of a long wavelength as being something that a long wavelength is something that corresponds to a big number. And now you're ready to move on to part 2. So for the majority of this lecture, we're actually just going to be on a pen and paper. So I'll video that as a separate video, and then we'll come back and